All right, let's do some Physics 1. So, unfortunately, only the J version of the question gets released each year. I know a lot of you got a different form, but unfortunately, we can't talk about those. Looking at this set, this is like the primary US East Coast set. It looks definitely harder than last year, but it was still very fair, and there's a lot of points that you can earn here. So we'll just work through it. So, first question, we see a water fountain getting launching droplets into projectile motion. So this looks like a fluids question at first, but you'll see it's really just kinematics most of the way through. So after a time tf, a droplet is fully traced out this parabola here. We're given its max height. First, we want to sketch the horizontal and vertical components. So again, I'm going to solve these out and give my best guess as to where the points are distributed. So horizontal velocity component, well, we can think about this with like a dot diagram. So maybe I'll take a couple dots here. So we know that vertically, you're going to begin moving pretty fast vertically. Then gravity slows the projectile down, stops the projectile at the top, and then turns it around and speeds it up. Then horizontally, though, gravity only acts vertically, so you get absolutely zero change in your horizontal velocity. So that's because, again, we know that acceleration is directed downward at all times. So our graph, this is just a classic projectile motion graph. We have a constant horizontal velocity, and then we have a vertical velocity that starts large and upwards, then it hits zero, then it's large and downwards. So this would be a line with negative slope. Now there's no grid, so we can't really grade you on anything about values. So flat line gets you A1 for horizontal, and negative slope gets you the point for A2. I can't really imagine it being anything else. It has to go negative. I think we have to have a negative slope, and the line has to dip below the axis. All right, speed of the water exiting the nozzle. There's two approaches here, so I think I'll show both just because we have time. Now, the first thing I would do is I would just do this like a projectile motion kinematics question, because we were given this this setup where we're given just the angle and we want the launch velocity. So this is just our standard decomposition, where if you have a projectile and this is your angle, we know our vertical component, which is the one that's influencing the height, is v sine theta. So we can just do kinematics with that because we know our delta y, we're going to climb a distance h. Our initial y velocity is v sine theta. Our final y velocity, which is the peak, would be 0. Acceleration would be g, downwards. And the t is not given directly. Oh, that's an interesting way of doing it, too. There's an interesting free fall way you could have also done this using some symmetry. But we will just plug in to the time-independent kinematics. So I get 0 squared equals v0 sine theta all squared plus 2 times negative g times h. Then we can bring that up and simplify. And we'd get v0 squared sine squared theta equals 2gh. Divide both sides by sine squared theta. And take a square root. You can definitely simplify this, but I'll just keep it in this form. So let's see. In the derivation here, it's worth 3 points probably. So you get a point for like decomposing. I imagine that is a point for decomposing the vertical into b sine theta. Or sorry, it's still a. This would be a3. You get a point for kinematics, and you get a point for the final answer. Now there is an energy solution. You just have to be a bit careful. You could say the energy at the start is equal to the energy at the top. Energy at the start would be 1/2 times the full velocity squared, and energy at the end would be 1/2 times mv squared of the x velocity, because at the top you are still moving, it's just in the x only, plus mgh. Because remember, you don't totally stop at the top in a projectile, you're still moving horizontally. So you'd end up solving this equation, which doesn't look like it's going to give the right answer, because if you look at the decomposition, your x velocity has cosine in it, but it actually does work out because you have to use the Pythagorean identity, where you'd get 1 minus cosine squared, which is sine squared. So energy works too. I imagine you'd get a point for energy, and you get a point for like the right equation, and then you get a point for the right answer if you did energy. So that's that. The nozzle has a circular cross section. Derive an expression for the flow rate. So this is an equation from the sheets. This is the only fluids connection. Flow rate is equal to area times volume. Well, we have a circular cross section. So area of a circle is pi r squared. And then the velocity we just solved for. 2gh over sine squared theta. I think they're going to be a bit more picky here. I feel like, actually no, I feel like you get a point for a substitution or a statement of flow rate is AV, and then I think you get a point for pi r squared. Pi r squared is definitely one of those points. So that's your 7A points. And then we have the conceptual part. So we replace the nozzle with a new nozzle of smaller radius and same angle of launch, but it says the flow rate of water is the same. So that's our key detail here, is that flow rate, which is equal to AV, is a constant in this problem. And it says that we're just shrinking the radius. So I'll show you my answer that honestly would probably get all 3 points. But I'll show you my typed out one too. So this was my reasoning. It's better just to reason through than justify. So I noticed that AV was equal to a constant. And I also noticed that if R decreases, area decreases, because area is related to radius squared. So this means that if area decreases, then launch speed must increase to maintain the same flow rate. So if V goes up, kinetic energy goes up, so the final gravitational potential energy goes up, so H reached increases. So that's my outline of a solution. And honestly, I am almost 100% confident this earns all 3 points as long as I end it by selecting the new height is taller. But here's how I formalized it using a lot less equations. Decreasing the nozzle radius decreases the area. Since flow rate equals AV equals constant, a higher speed is required to compensate for lower area. So the water is being launched at a higher speed. The droplets have greater kinetic energy and will therefore reach a greater height than before, while the kinetic energy is transformed to gravitational. So you get a point for the checkbox. then you almost certainly get a point for this, for having to say that like A and V are inversely related if flow rate stays the same. And then lastly, you get a point that connects increased velocity to increased height. I saw people online also did this just with kinematics. They said, well, if you have more velocity, you have a larger vertical component, so it takes gravity more time to stop you, so you get to go higher. That works too. There's usually lots of conceptual explanations, so don't assume that mine are the only one. We're usually pretty generous if you're doing good physics. Unless if it tells you, you must reference X, Y, or Z. All right, that wasn't bad. And usually the MR is the hard one, because it's just symbol math, symbol math, symbol math. But that wasn't bad. All right. Now I got the TBR. So we have a mass that's going to hit another mass, and it says after the collision, the incoming disk bounces off at half its initial speed, just in the other direction. Now, actually, this is where I'd pull up receipts. If you looked at my free response practice test for AP1, my QQT used this exact mass ratio, and two of the parts are almost identical. So I'll consider that a win for my predictions market here. And of course, if we have things colliding, we're going to be interested in solving stuff. But this is the TBR, so we should read A, B, and C first. This is a nice representation. We have a momentum diagram where it shows the momentum before the collision with vector arrows, and we got to draw it ourselves after. Then B, which is entirely independent, determine the kinetic energy of the other disk after the collision. Part C has us graph the position versus time of each of the disks and their shared center of mass. So it's kind of an interesting choice. And then part D asks us to compare impulses, but part D should always come last. A, B, and C are the sort of storylines in parallel thing. All right, so what do we know about momentum? Well, we know that anytime things are colliding, unless if there's like weird hinge forces, and it's a rotation thing, the linear momentum stays constant in a system. So this means that total momentum before has to equal total momentum after. So disk R, before the collision, it said impacted at V0, and disk S was not moving. And this mass was M0, this mass was 3M0. So momentum is mv. So it says this vector represents just mv. So mv0 is with 1, 2, 3, 4 ticks. So every unit of mv is worth 4. And if I sum up my total momentum, we see that it's 4 plus 0. So all of my momentum arrows must add up to 4 in the end. So now what we are given is that the mass 1m moved in the opposite direction at v over 2. And we don't know what happened to the 3m yet. So I need to make my momentum arrow in the opposite direction and half as long. So this momentum, I like to use red for my solutions. So this momentum represents m times negative 1/2. This would be negative 1/2 mv0. And this corresponds to negative 2 units. So now by momentum conservation, we can see that if the total momentum was originally 4 arrows to the right, and I have to get to 4 in total, well, that must mean that this vector arrow must be 6. Oh, how convenient that this was the extent of this scale. So we can actually see here that I must have had positive 6 units of momentum here. And we said that every mv0 was worth 4. So actually, if you work it out, not that this is necessary, you'll see that this is 3/2 mv0 worth of momentum to make it work out. So actually, you could totally solve the part B collision part using this representation, which is pretty cool. So how do you get the points? Well, I feel like the third point is just the sum of momentum is constant. So getting 4 arrows overall. Then for A1, it might just be drawing a, I think it's drawing a, I think you have to get it right, honestly. Yeah, I think for A1 it has to be just an arrow that's 2 units left. You probably have to get that one correct. And then A2 would probably be maybe just a rightward arrow. And then the magnitude is kind of reflected in the A3. That's kind of my prediction there to not double ding you. So I'm not sure if you're going to need the length of that to be correct. Because if the length is incorrect, it's going to knock you out of A3. But we're definitely going to make A3 a point because the point is conservation. That's my guess there. All right, now for the derivation piece. Starting from conservation of linear momentum, so we need to use that. Derive an expression for the kinetic energy of disk S. That's the 3m one. So conservation of momentum. Momentum before equals momentum after. Before, we have a disk of mass m0 moving at a speed of v0 to the right. And then stationary other disk. Then that single m rebounds at v over 2 in the other direction. And we don't know the speed of the S disk. So we get mv0 equals negative 1/2 mv0 plus 3m vf. So we get the result from earlier that 3/2 mv0 is the momentum of the larger disk. And we can cancel the 3. And we get the v of that disk is just positive 1/2 v0. But we actually want to find the kinetic energy. So now it's just a substitution. And the k equals 1/2 m v squared. So I get 1/2 times 3m0 times v0 squared over 4. And I get 3/8 mv0 squared. All right. Conservation of momentum is B1. Setup is B2. Speed after the collision is B3. And a correct substitution into kinetic energy is B4. I'm not necessarily sure your B4 has to be right to earn that point. Hard to say. All right, now for our graph. So all of these velocities before and after the collision are constant as they move. So we can just say that x is equal to vt. So we just got to figure out how the velocity changes, and that's going to change our slope. So the easy one is actually center of mass, because center of mass is constant velocity in any closed system. So the center of mass line does not change, and it just stays at its constant velocity, because the center of mass of the system can only have its motion altered by external forces. And then disk, we know that from our math, both disks actually move at the same speed after the collision. We just have different directions. So we have negative v0 over 2 and positive v0 over 2. So disk S, which was originally stationary, actually it's probably easier to do R so we can try to get the slope right. So for R is going to reflect. So that would be like a pure reflection, but its speed is going to half So I get this. So we'll call this one R. And then we just need to make the S1 symmetric. Because disk S starts moving at positive V0/2. This is actually quite tricky. I imagine you just get each of these right and you get a point. The graph is kind of tricky. People forget the center of mass motion idea. All right. During the collision, the magnitudes of the momentums of each disk are delta PR and delta PS. Well, what is impulse? We have to reference a fundamental physics principle. So delta P is m delta V, or it's F delta T. Now, this does not seem like a very conceptual approach, but F delta T does. Because again, what's happening? We have two blocks colliding with each other. And if you're colliding with each other, we have equal and opposite forces. So we know that delta P equals F times delta T. The contact time between the disks is the same because they're in contact with each other. That's just kind of by definition of being in contact. And then we have the same F by Newton's third law. So if we have the same force for the same time, just with opposite directions, this means impulses will be equal and opposite. Now, there's another one that doesn't cite Newton's third law that you could have also done that I'm just thinking of right now. Make sure you make your selection. Now, your other one you could say is you could say the total momentum change of the system is 0. So any momentum gained by S must be lost by R. So if you say that, that also gets you D2 by saying that since the net impulse must be 0, the impulses delivered to each disk are equal and opposite. This was a pretty fair TBR. I actually asked almost this identical question on mine. I just talked about forces instead of impulses. So I did a decent job of predicting this question to show up. All right. We're going to show you just how much you overwrote for the lab question. Group of students investigating friction. They have only a meter stick, and they drop a block on a frictionless ramp, and it stops on a friction more surface. Got friction less. Here's friction more. We want to find this mu coefficient. Well, the only thing we have is a meter stick. So we must measure distance. And we can't graph one thing, so we have to measure two distances. So here's how much you overwrote. This gets you both 8 points. We're going to measure the release height h. We're going to measure we'll call it the horizontal stopping distance. The horizontal stopping distance, x. And then we will repeat for various, no, I'm so bad at that word, various values of h. So to get A1, you have to say measure height and horizontal distance. If it's clear from context, I'm sure you got it. And uncertainty is anything about multiple trials, although you want to make sure you're varying a variable. Because you can't graph, like, if you drop from the same h every time, you're probably not getting a graph out of that. Although I wouldn't discount the chance that you get that point. And also, if you wanted to make it extremely unambiguous, you could draw yourself a little setup and show that this is what you mean by h, and this is what you mean by x. It's like the stopping distance. All right, so now let's analyze it. How can we make a graph? And how can we get mu from that graph? Well, anytime you see height change, it's probably energy. So if we think about energy, when we're at the top of the ramp, the energy of the system is mgh. When we're stopped, all of our energy is gone. So it must have been turned into work from the frictional force. So we can just say our mgh got turned into work from friction. And friction is going to be mu k times the normal force times the distance that the frictional force acts over. Because work is Fd. So we get mgh equals mu k, normal force on a flat surface, mg, times d, or in this case, x. Goodbye, mg. So we get h equals mu k times x. Now here's how you can earn both B points instantly. H, no transformations. That goes on my y. X, no transformations. That goes on my x. What's in front of my x? Well, that's just the slope. That earned me both B points. So B1 is the linear relationship. B2 is the analysis. Now, you could have graphed any variant of this. If you said graph x versus h and the slope is 1 over mu, that works. You just had to be very clear what goes on what axis. So this is always my tight and true approach to getting both B points at once. Now we have an experiment where we drop a block along a friction-full inclined plane. We have its speed after different distances. We have this absolutely beautiful expression to linearize with. Thank you, College Board. It's definitely linearizable already. It does say they put d on the horizontal axis. So we get v squared equals 2g sine theta minus mu cosine theta times d. And it says that we already put the quantity d on the x-axis. So it's pretty easy, therefore, just to say that v squared should go on the y. I should make my colors consistent here. And then that means that this entire expression is my slope. Now, that's not a problem because g is g. Sine theta, well, theta is 30 degrees. So sine theta is going to be a half, and cosine theta is going to be root 3 over 2, which is 0.87, I think, when I did this earlier. So and g is 10. So all that's missing is mu from the slope if we find it. So now is our time for your daily scheduled off-camera mining joke. Boom, there's v squared. And magic. Snap our fingers. Boom. Here's a linearized graph. Now, this was actually a really easy scale for me to do. So I actually did like the choice of values here with v squared. It works out nice. So how do you get your C points? Well, C1 is probably graphing some form of v squared on the y. Could you move some constants around? Maybe you put 2g in the denominator. But yeah, you probably had to have v squared on the y because d was fixed on the x. C2 is the scale plus the units, right? Linear scale plus units. So you had to correctly square meters per second. Then C3, easiest point on the whole test. You got to plot points. Time consuming though. Then C4 is the best fit line. So if you graphed random stuff, you can still get C2, C3, C4 as long as you have right units, plotted the points, and you best fit lined it. Then I did linear regression with Desmos to find the slope. You could have totally just done it by hand and just said rise over run. If you did rise over run, I'm sure your slope is close to 0.5. Just make sure you're using the line and not the data points. You can't take the slope of data, but you're going to take the slope of a line. So I get my slope is equal to 2g sine theta minus mu cos theta. That's what we said earlier. That's actually how you get d1. You have to relate the slope to the best fit line. No numbers yet. Then we do a substitution. This rounds to this. And then we do a substitution. So that's that. Then we just do some algebra steps here. And we get mu is 0.55-ish. I have no idea what the range will be for like acceptable values of mu, but you have to get the number right to get D2. If I were to guess, it's probably like between 0.5 and 6 or something like that. Who knows? Yeah, I'm not totally sure. So lab question was pretty reasonable, even though there's a bunch of garbage in the slope this time. All right, now for the QQT. This looks really scary. Like, this is a really scary looking diagram when you look at it. But it's actually a very standard problem with like one twist. So we have these like spinning top toys. We have a string that's wrapped at a radius r. And it's the same length of string. So it says we pull all of this unwrapping string of the same length across these toys of the same radius. And then they're left to let go and spinning. And it tells us that toy X has a larger rotational inertia, which makes sense because if we look at this picture, there's a lot more of toy X that is out, right? We said rotational inertia increases if your mass is farther away. And we are going to be interested in comparing the angular speeds of each toy after the string unravels. This is the top view. So you see we're just applying a force at a constant radius until all of the string of length L unwraps. So which speed is greater? Is the speed greater for the toy with larger inertia or with less inertia? Well, given that fact and just what the word inertia means, we can probably think that it is going to be the one that is easier to rotate. Now, here is my like semi-quantitative explanation that I still think probably gets full points, and you'll see my typed version. So what is causing the rotation? Well, it's the torque. So notice torque, which is RF, is the same for both toys. It's the same string, same radius, same force, same everything. So we have the same torque on each toy. But since y has less inertia, since toy y has less rotational inertia, which I'm going to call I, y has greater angular acceleration, reaching a greater speed. Now, when I typed it out, I said this: torque on the toy is the same, nx over the same angle, or same string distance. Since toy x has a greater rotational inertia, toy x accelerates less under the same torque. Thus, for a set angle, toy x will have a lower increase in angular speed than toy y, so omega y is larger than omega x. Now, there's a million ways to justify this. I can't imagine all the different rubric variants that there are. So for my variant, I would say you get a point for saying the torques are the same, and you get a point for saying that something like if you have a greater inertia, you get less acceleration, or something like that. Now, if you did energy, you could say the torque is the same. I think you need to say that again. You probably get A2 by saying just the torque is the same. So the work done is the same on both toys, and that's getting turned into kinetic energy. But if you have more inertia, that means you can create the same kinetic energy with a lower rotational speed. So there's definitely an argument that says like k equals 1/2 I omega squared. And if k is constant, if you have increased rotational inertia, your angular speed must decrease to compensate. All right, now for the derivation. So I like Newton's second law for this, but work energy works too, and I imagine we'll just do both. So starting with Newton's second law, this says that the net torque is going to be equal to I times alpha, and we are driving the speed omega x. So the torque is just RF. Are both of those subscripted? Yes. Equals Ix times alpha. So alpha would be equal to RF over Ix. Then we have an acceleration and we want speed, so this is kinematics. So we can just do a kinematics laundry list. We don't have the time, nor do we care about it. We do have the angular acceleration. We want the final angular speed. We start from 0. And what is our delta theta? Now, this is the one twist with this problem, is we have to find the theta. So what we're given, actually, is that the length is equal to L. So we have to use this relationship that arc length is equal to R times theta. So the theta is actually L0 over R0. That's kind of tricky that you had to do that arc length conversion, because it seemed weird to some people that R was actually not in this. It was the string length. So people forgot that you had to convert the length into the angle. So then we just go ahead and plug and chug. No time means we use this one. All right. The R0 does actually cancel, so we get omega squared is equal to 2 F0 L0 over Ix, or 9, if you will, for those Roman numeral users. So we can take a square root and get this. Now, if you used work energy, it's arguably a lot easier, because you could just say work done is equal to delta K. And I'm just going to draft the solution because we already saw the details of one. So the work done for angular forces would be the torque, which is RF, times the angle that it acts over, which we said was L over R. And delta K would be 1/2 I omega squared minus 0. And we see it is going to be equivalent. So how do you get your points? I think you get a point for multi-step with Newton's second law or energy. You get a point for the angular acceleration, probably. That seems too easy. Maybe it involves theta. Maybe you need to know theta. But it's probably just the angular acceleration. Then you get the correct answer. Now, if you use energy, I feel like you need a correct expression for like the work done. So this is B1. B2 is probably this entire left-hand side, maybe. And then B3 is the answer. Hard to say. It's probably easier than I think to get the B points on this. Now, is it consistent? Well, it is consistent. Because we said that omega y is larger. So we said omega y is larger. So what is the real change here? Well, it's the same force, same length, but rotational inertias are different. So x has a larger rotational inertia than y. So omega x is smaller than omega y since I appears in the denominator. The denominator. Right, because if something's in the denominator, that means increasing the quantity decreases the output. So I think obviously you just had to say if it was consistent or not. And then C2 is like functional dependence. So you just have to say like I is in the denominator. So if I is bigger, omega is smaller, something like that. Yeah, that's pretty fair for P1. Can't really complain too much about that. If you got a harder form, than this, don't feel bad. The curves are all different, so it's all dependent on how people are doing on your form. So everybody had these 4 questions that took one form, but everyone might have also had a different 4 of different difficulty. So they look at the curves separately. What do I think is like a 5 on this? That's probably a question I'll get a lot. Last year was like 80%. This year's questions are definitely harder, but I still feel like it's going to be close to that 80% mark. Yeah, that's kind of my initial reaction. We won't know until the reading, though. If you have any questions about solutions or things, definitely let me know, and I'll give you my best answer. All right, cool.